Hi everyone, my name is Fazluddin Ahmed and I'm a first year PhD student working with Dr. Wang. Today I'll be presenting my CS701 project, which is real-time protection of JVM based application against remote code execution attacks. So what exactly are we dealing with? Remote code execution, or RCE, is the most severe class of vulnerability which lets an attacker execute arbitrary commands on your system with a single request. And this isn't anything theoretical. It is a real-world vulnerability which affects Java's ecosystem. Frameworks such as Apache Struts, Spring, Log4j, ActiveMQ, they are all victims of this vulnerability, and the real-world impact is massive. For example, back in 2021, the Log4j vulnerability affected millions of applications all over the world. And in 2017, the Equifax breach exposed more than 100 millions of records. So the outcome of these attacks is always the same, which is full server takeover, data exfiltration, or ransomware deployment. Now you might ask, don't we already have existing defenses for this? The answer is yes, we do, but they all have some sort of fundamental gaps. For instance, firewalls and antiviruses, they operate at the network or the system layer. They have no idea about the JVM, and there could be encrypted or obfuscated payload, which can bypass them easily. Then there is patching. So patching is a reactive approach in which you are always one step behind. And there could be 0 days vulnerability, 0 day exploit, which can exist right before the patches do. And modern Java applications have such dependency chains that makes the patching impractical. Log4Shell provided that at scale. And if you want to fix the source codes, then it simply won't work when you are dealing with multiple third-party libraries or closed source applications. So we need something different, something that is the last line of defense and that works regardless of which vulnerability is being exploited. Now, let me show you concretely on how one of these attacks work. So this is the Log4Shell vulnerability. In this attack, the attacker injects a JNDI lookup string into a field that gets logged by Log4j. So it could be a user agent header, it could be an HTTP form input, anything. Now, the Log4j's message evaluation feature looks up the string and it evaluates that as an expression. So in this case, it looks up the JNDI string and it calls an LDAP server, which returns a remote class from the attacker server, from the evil.com. And when this class gets loaded into the JVM, the malicious class, the remote class, it tells the JVM to run the arbitrary OS command inside it. And bam, you have the OS command injection attack taking place. Now, there's a different attack, which is the Equifax breach, CV 2017-5638. Now, in this case, the attacker sends a crafted content type header into an Apache Struts application. Then the application parses the header using the Jakarta parser. And when the parser fails, the application tries to generate an error message, but here is the main design flaw. The error message also gets evaluated as an expression, as an OGNL expression, which is an Object Graph Natural Language expression. It is used in Java for UI stuff. So when OGNL tries to parse this, the language tries to resolve it using the Java's reflection API and gets the getRuntime method. And then this getRuntime method is used to run the exec method, which triggers arbitrary voice command execution. And this is the key insight behind our work. So these attacks, no matter how diverse these attack vectors are, they all travel through different internal mechanisms like reflection, method.invoke, expression language evaluation, etc. However, they they all converge on two target APIs, which one is the runtime.exec method and the other is the process builder class. Now, when these calls pass through the JVM, the Java bytecode read them as invoke virtual instruction before they reach the OS command. And this is our choke point where we use Java bytecode instrumentation to catch every exploit, be it known or unknown. Now, our approach is based on the idea of Java bytecode instrumentation. It's a well-established idea. This technique is used in profiling, framework development, and lots of other cases. But in this case, we apply it specifically for security. Now, there are 4 properties that make this different from existing defenses. First, we don't need any type of signature. We don't need any prior knowledge of the attack or the vulnerability. So the second thing is we detect the attacks as soon as it happens in real time. Third, we are independent of the source code. We do not need any access to the source code. We don't patch the source code. It just works at the bytecode level. And fourth, it is the application. It immunizes itself. So once you have instrumented the application, it takes care of its own without relying on any third-party libraries or any external tools. Now, there are 2 ways to instrument a method in Java. The first one is caller-side instrumentation, where you place a hook at every call side. For example, if A, B, and C, they all call the runtime.exec method, you have to place the hook, you have to place the instrumentation code at each of those places. However, this method is not that much good because the runtime.exec method that are achieved using the Java Reflection APIs gets missed in this approach. So we rely on something which is called callee-side instrumentation. So in this case, we actually instrument the target method. We actually place our hook inside the target method. So in this case, if you want to call runtime.exec using direct call, using Java Reflection API or method.invoke, they all will call the runtime.exec method, and inside the runtime.exec method is where our hook lives, and then we will be able to catch each of these invocations. And then we do our instrumentation process in 2 parts, which I'm going to show you next. The first part is the static instrumentation. So in this phase, we take your application's bytecode and we process it using our tool. So in this case, we are going to look for the runtime.exec method, and we are going to replace it using some sort of a random secret method name. And this secret method name is generated once using the seed command of this tool. And the secret name is stored in a config file, the config.ini, which is used later. And the tool will give you output. If you are passing a class, it's gonna give you a modified version of the class file. It's going to give you a modified version of the jar or the var archive. The second part is the runtime agent. So it attaches to the JVM when you try to run the application. So it uses the Java agent flag to attach to the JVM, and it is a built-in Java feature. So it is supported in every major and every minor Java versions. And the agent will read the secret method name from the config file, and then it will monitor for any method that's get executed using this method. So in our application, we already replaced the runtime.exec method, right? So when the application tries to run the runtime.this method, this agent is going to replace this with the original exec method, and it's going to let it run. However, when an attacker tries to trigger the actual runtime.exec method, this agent is going to catch and report that. Why? Because we already modified our original application, right? There should not be any runtime.exec method, right? So this is how we catch the attacks. And here's a demo on how our tool catches the vulnerability. So let's see it. So this is the Docker file of the application, and this is the another Docker file for the instrumented version of the application. And this is the exploit script. Now we're going to open the terminal and see. So these are our files, and see if there is any Docker process running. So we can see that there are no Docker processes running. So first we are going to instrument the application, which is going to create a safe copy of this application with our instrumentation logic. It's done. Now you can see that here. Now let's build the Docker images. So we have built the Docker images. Now let's try to run the vulnerable application first. And now the application is running. Now let's go to the other terminal, and here we can see that there's a Docker container running that we just started. And we're going to see like if there are any files in the temp directory. We can see that there are just these 3 files. Now we're going to run the exploit script, and we are going to create a file called pond at this directory. We can see that there is the attack took place here, and there's some exception taking place. And when we check that, we can see that the file is created here. So we have already achieved our RCE here. Now let's try to create another file. Yeah, the attack took place again. And here's the file. The file is here. And now let's try to remove one of these files. Yeah, so the file is deleted. So we can easily perform RCE on the vulnerable application. Now let's clear that, and we are going to run the fixed version of the application containing our instrumented bytecode. And this is the config file. So this is the secret name of the exec method. And this is the log file. So currently it's empty. Now let's run that. Here we can see that our agent has successfully loaded and it's ready. Now let's go back to the other terminal and run the exploit. So the Docker container is up and running. Let's see, there is just 3 files. Let's try to run the script. Okay, and let's see. So we can see that there are still those 3 files. Nothing got created. And here in this terminal, we can see that our tool has already caught the invocation of the external attack, the RCE attack here. So we can see the call chain here, and the runtime.exit method was blocked here. Now, to validate our tool against real-world vulnerabilities, we developed a collection of 24 high-severity RCE vulnerabilities. So they span a wide range of Java frameworks and attack vectors. And each of these vulnerabilities have been set up as Docker's environment with an exploit script so that it can be easily verified whether the instrumentation blocks the attack or not. And as of this moment, we do not cover native JNI calls, which goes directly to the OS. JVM scripting engines such as Juvie and Nashorn have their own execution part, and they are not yet supported. And the Android runtime, which is Dalvik, is not currently supported yet, and we intend to address these in our future works. And in our future work, we try to cover the gaps that I just mentioned, and hopefully we will try to extend this model to other types of vulnerabilities. So that concludes my presentation, and this code is currently private but should be available on GitHub at some point. And please feel free to reach out at my email. Thank you.